My name is Zhong and I'm a student from Northeastern University of China. My topic today is an optimized method for massive sensitive data classification in an industry environment. Fourth Industrial Revolution is popularly understood as the transformation of traditional manufacturing into intelligent manufacturing. Industrial Internet is the technology using Internet of Things for large-scale industrial manufacturing. The idea behind the industrial Internet is intelligent industry based on big data, which can process and transfer data more accurately, save costs for large-scale manufacturing enterprises, and achieve the optimal efficiency of industrial output. Large-scale manufacturing industry chain is a complex network chain consisting of a series of different types of enterprises. Each enterprise as a data source constantly generates massive and heterogeneous data in all stages of the industrial chain, which is of great value in industrial chain management. And there are many enterprises and departments involved in the industrial chain network, and there are not only cooperative relations, but also competitive relations between different enterprises, which brings challenges to data sharing among enterprises. On the one hand, all stages of the industrial chain urgently need transparent access and sharing of key information, such as production information, to reduce costs, improve enterprise cooperation efficiency, and solve the problem of information asymmetry between upstream and downstream enterprises. However, on the other hand, there is a competitive relationship between core enterprises in the industrial chain, such as suppliers at the same level. Enterprises do not want private data, such as trade secrets and financial information, to be obtained. So, how to ensure the necessary transparent data access and sharing between enterprises and realize the protection of some private data is an urgent problem to be solved. As mentioned before, with the continuous progress of science and technology, the era of big data has arrived. Although big data brings a lot of convenience, the huge information base also brings some difficulties for accurate information screening. Therefore, the effective classification of data is an important means to improve the efficiency of data governance. Data classification sets labels and categories for a given data type. In the problem we are considering, these types will be used to set the sensitivity level. Sensitive data refers to data that is not known to the public and has actual or potential use value. When sensitive data is lost, used improperly, or accessed without authorization, it can cause harm to society, business, or individuals. As mentioned before, after years of informatization construction, large-scale manufacturing industrial chain has accumulated a large number of enterprises-level data, including customer data, marketing and sales data, production data, and other important sensitive data. We can also understand the importance of sensitive data classification from another perspective. With the large-scale use of network data, a little carelessness may lead to data leakage. And once this sensitive data leakage, it is bound to bring inestimable losses to enterprises. If all data are set to high sensitive level without data classification, it will lead to high operation complexity and high cost in the protection of data information security, and it greatly reduces the efficiency of enterprise cooperation. However, if all data is set to a low sensitivity level, the leakage of important private data will lead to the acquisition of sensitive data by attackers or the use of malicious personnel to engage in business transactions and steal personal privacy, which will cause unpredictable losses to the interests of enterprises and employees. Therefore, sensitive data should be properly classified and categorized as needed. To solve the above challenges, we proposed a sensitive data classification method based on improved ID3 decision tree. This model can synthesize various data features to make the final classification while keeping concise structure. Decision tree algorithm is one of the most basic and effective algorithms in artificial intelligence and machine learning. Firstly, the decision tree algorithm uses a mathematical analysis model by training and mining rules of random and disordered sample data and obtains basic classification rules and then makes classification on the target dataset. ID3 is a classical decision tree algorithm with simple ideas and strong learning ability for sample features. Generally speaking, the construction of a decision tree can be divided into two parts. One is the feature selection of the nodes of the decision tree. The other is the tree construction. We focus on how to select the node features, or namely the node attributes of the ID3 decision tree. In general, the criterion of attribute selection of ID3 decision tree algorithm is based on information gain theory, which provides criteria for the selection of attributes of each decision node. After selecting node attributes, the sample data are classified according to different attribute values under the attributes. The core of the algorithm is information entropy, which is defined as the formula. We assume that the dataset is D and M is the number of attribute values of decision attribute AD in the dataset D. And in this topic, AD is the sensitivity level, and PI is the occurrence probability of the I's attribute value AI in the decision attribute AD. Information entropy is used to calculate the purity of the data in a sample set, which represents the number of sample categories contained in this node. And as can be seen from the formula, the greater the information entropy, the lower the purity of the sample, and the more the sample categories. On the contrary, if the information entropy is smaller, it means the purity of the sample is higher and the sample data has fewer categories. Information gain is the change value of information entropy of sample data before and after attribute division, which can be used to measure the difference of information entropy in probability distribution. Assume that int AD is the weighted sum of information entropy of each subset divided by conditional attribute A. Suppose n data subsets are generated after the partition of conditional attribute A, and the number of data items contained in each subset is S1, S2 until Sn, and the definition of int AD is given in the following formula. The definition of M is the same as M in the previous formula and is the number of attribute values of decision attribute AD in dataset D, and μi is the weighted coefficient of information entropy of each subset, which is defined as the formula. Then the information gain divided according to attribute A is defined as follows. ID3 algorithm calculates the information gain of each attribute through the information entropy and takes it as the partition standard. According to the value of the information gain, it compares which attribute to select for node splitting. Each node selects the attribute with the highest information gain value, and this process is repeated until the information entropy of the final sample set is 0. ID3 algorithm is simple and feasible, and the process is intuitive and clear, and it can train the classification model well for most discrete data. In the ID3 algorithm, each node selects the attribute with the largest information gain value as the split attribute. From the above calculation process, it is easy to see that such selection criteria tend to ignore the attributes that are important for decision-making but have few values, namely the multi-value bias defect of ID3 algorithm. Aiming at this shortcoming, we proposed an improved ID3 algorithm based on attribute weighting. In order to ensure the rationality of the obtained weight coefficient, the correlation coefficient is used as the attribute weight coefficient. The correlation coefficient reflects the closeness of the relationship between random variables, and its value is between -1 and 1. And in the same sample space, the closer the magnitude of the correlation coefficient between attributes is to 1, the higher the degree of correlation between attributes is. Therefore, the significance of correlation coefficient can be used to calculate the correlation weight between attributes. Suppose that AC is a conditional attribute and AD is decision attribute, then the correlation coefficient between attribute AC and attribute AD is defined as shown in the formula. And co-ACAD is the covariance of AC and AD. DAC is the variance of AC and DAD is the variance of AD. Thus, the correlation weight of attribute AC to decision attribute AD can be obtained. Therefore, according to the characteristics of ID3 algorithm, which selects maximum information gain as the basis for splitting and the significance of correlation coefficient, the original formula is improved to the new formula after attribute weighting. And as can be seen from the formula, the larger the attribute weight lambda, the greater in the influence of the conditional attribute on the decision attribute, and the smaller the coefficient multiplied by int A, and so the greater the information gain. The sensitive data classification based on the improved ID3 algorithm proposed mainly consists of 3 parts: data pre-processing, feature selection of decision tree nodes, and decision tree construction. Sample selection should be representative, typical, and complete. We classify sensitive data into 4 levels: public data, external sensitive data, internal interdepartmental sensitive data, and internal inter-department sensitive data. In order to improve the classification accuracy, the data sets are divided into training set and test set according to the ratio of 9:1, 8:2, 7:3, and 6:4, respectively. The training set is used to complete the construction of the decision tree, and the test set is used to test the performance of the constructed decision tree. After experiments on training sets of different sizes, it is finally found that The datasets divided according to the ratio of 7:3 can make the decision tree model achieve the optimal classification effect. And there are many numeric attribute values in sensitive data. In order to facilitate the establishment of the model and improve the computational efficiency of ID3 decision tree, we transform the non-numerical feature parameters in the original sensitive data into numerical feature parameters. For example, in the original sensitive data sample set, the feature value of safety feature in the data is of taxa type with 4 degrees, low, medium, high, and very high. Then we convert them into numerical types accordingly. That is, convert them into low to 1, medium to 2, high to 3, and very high to 4, respectively. And as mentioned before, the feature selection criterion of ID3 decision tree algorithm is based on information gain theory. According to the improved ID3 algorithm we propose, by calculating the information gain of each attribute based on attribute weighting, the attribute with the maximum improved information gain is selected as the attribute of the current node. This has been said in detail, so I won't repeat it here. The core stage of decision tree algorithm is the tree construction process. Suppose the training set D has M attributes. For the improved ID3 algorithm proposed, its construction process is as follows. Step 1, construct a node. If all samples are on this node, stop the algorithm and change the node into a leaf node and mark it with this class. Step 2, if all samples are not on the same node, work out information entropy of each attribute, figure out improved information gain, and then select the attribute with maximum information gain as classification basis. And step 3, assume that the attribute value of AJ has V different discrete values. Create a branch for each value and divide the sample set D into V subsets. Step 4, repeat step 1 to step 3 until all attributes are used up. In the process of tree construction, we exclude the special case of step 1, and we judge all attributes in the attribute set, select the optimal attributes for division, and delimit subnodes for on different attribute values of the optimal attribute according to the sample data. After the current node completes data partitioning, the attributes that have been partitioned in the previous step are removed, and then generate data subsets and continue a new round of partitioning. Until the dataset is undivided, the decision tree stops growing and finally returns a complete classification decision tree. Generally, the performance evaluation of decision tree classification models is mainly carried out from the following 2 aspects. Number 1 is accuracy. And accuracy refers to the ability of the decision tree classification model to accurately predict the target category of new or unknown data. The accuracy of prediction is related to the number of samples in training set, decision attributes, attribute values, and the distribution of samples. Number 2 is robustness. Robustness refers to the ability of the classification model to accurately classify the dataset in the case of incorrect data and incomplete data. In real life, data collection will inevitably have incomplete data, data error, data redundancy, and other phenomena. So the constructed decision tree classification model needs to have a good ability to deal with this data in order to avoid affecting the performance of the classifier. The table shows the classification accuracy of each sensitive level of data. As can be seen from the table, the accuracy of the classification results of each sensitive level is very high, which can meet the needs of the industry. The figure shows the classification accuracy of the traditional ID3 algorithm and the improved ID3 algorithm we proposed on the different training sample set size. As can be seen from the figure, the accuracy of ID3 decision tree algorithm is improved after attribute weighting. In order to verify the robustness of the improved ID3 decision tree algorithm in this paper, error-sensitive data of manual intervention is added for training under the same dataset size, and the experimental results are shown in the figure. It can be seen that the robustness of the improved ID3 algorithm is higher than that of the traditional algorithm, when the proportion of error-sensitive data is less than 8%. However, when the proportion of error-sensitive data is 9% and 10%, the robustness of the traditional ID3 algorithm exceeds that of the improved ID3 algorithm. We believe that the reason for this phenomenon may be that the excessively high noise data makes the calculation of attribute weights deviate, which affects the selection of attribute of each node and deteriorates the classification results. In addition, we also verified the robustness of the proposed algorithm from the perspective of data sources. Both weather and DNA datasets are selected for training, and experimental results are shown in the figure. According to the figure, in the case of 4 different datasets, the improved ID3 algorithm proposed has stable classification performance, that is, good robustness. Compared with the traditional method, the improved algorithm also has higher accuracy, which further verifies the performance optimization effect of the algorithm. The sensitive data classification based on improved ID3 decision tree algorithm by our invention realizes the maximum utilization of sensitive data generated by large-scale manufacturing industrial chain in big data environment. While making full use of information in sensitive data, it prevents irreparable loss caused by the leakage of important sensitive data, which is of great practical significance. According to experimental results, the branch accuracy of information of improved ID3 decision tree algorithm for sensitive data can reach 98%, which is significantly higher compared with traditional ID3 decision tree. In addition, it can still meet industrial needs with good test results even in the case of artificial error data added. And my presentation is over.